All right. How is everyone doing today? Good? Good? Excited for break? Yeah, that's nice. All right. Does anyone have any questions before we get started? All right. So there was a request to have the quiz open today, which I am fine with. So the quiz is open today through Monday. So I didn't shorten it. I kept it still open until Monday. So you can either take it early or late or at any point over fall break. So that'll be for quiz 5. And then quiz 4, I just unlocked so you can view the results of quiz 4. The average was really good. So it was in the 80s. I think it was an 81%, which is awesome. So yeah, we left off looking at our elimination reactions. And so we had started with E2, and E2 was our one step that meant that both our substrate and our base were involved in that rate determining step. So it's going to be leaving group leaves as our base attacks. And we had said that we had this stereochemistry requirement for our E2 reaction where you must be anti-periplanar. So that means that you must have your hydrogen and your leaving group 180 degrees from each other. They must be on opposite sides. The reason why was because of orbitals. Just like with our SN2 reaction, you need to have access to that sigma star. Where you access that sigma star is on the back side of where the leaving group is located, on the opposite side. So that's where we were accessing the sigma star, is where our hydrogen is parallel on the back side. So that's why we need to have that anti-periplanar alignment, is because that's where we access the orbital to break the bond. So when we look at our stereoselectivity, if you have multiple beta hydrogens, you're just going to make sure you always make the most stable alkene. If you have one beta hydrogen, one hydrogen on the next door to where your leaving group is, you must draw the Newman projection to know if your product will be E or Z. So to know what the stereochemistry of your product will be. So when I look at this starting material, I could imagine that I could have so here's my leaving group. So I only have one hydrogen there. So I need to have the hydrogen 180 degrees from the leaving group. So if I think about that Newman projection, if I rotate this to get my hydrogen and my bromine to be in plane with each other so that they are now aligned, and I am looking down this bond, that is where I'm seeing the hydrogen straight down, the bromine straight up. And what I like to do is I imagine this is what I'm deleting, right? I'm taking away that hydrogen and that bromine, but it's anti-periplanar, so I can. And when I take that away, I'm going to put my double bond in where it was located. So that means that I'm going to have the methyl in the upper left, the tert-butyl in the lower left, the benzene in the upper right, and the hydrogen in the lower right. So I'm going to delete it, put in that double bond, and put everything else in exactly as it's located in space. So that now I see that that is the stereochemistry that is required in my product for my alkene. So when I look at this product, is that E or Z? That's E. So my high priority groups are opposite each other. So that is E. So this is E is going to be my only product. I am unable to make the Z because my hydrogen has to be anti-periplanar, the bromine. So I must be 180 degrees from that leaving group. This is the only way to get it 180 degrees, is to have this conformation. So if I imagine, all right, let's invert that stereocenter. so that now I'm R instead of S. So now, when I go to take that hydrogen, that bromine, I get benzene is in the upper left, tert-butyl is in the lower left, methyl is in the upper right, hydrogen is lower right. My high priorities are now on the same side, so that is a Z alkene. So now Z is the only product. So if you have only one beta hydrogen, you just have one hydrogen next door, one hydrogen to pick from next door, you must look at what your three-dimensional arrangement is when it's antiperiplanar to know what the stereochemistry of the alkene product must be. Because the stereochemistry of the beginning is what's going to control the stereochemistry of the end. And as I said at the beginning, if you have multiple beta hydrogens, meaning you have multiple to pick from, multiple hydrogens next door, then you will always get the E or trans product as your major product. Because what you're going to do is if you start out here and I see that I have these Gaussian interactions, I'm going to rotate this structure so that I have the other hydrogen antiperiplanar. And now I'm going to have, I still have two, but I have a smaller Gaussian interaction because that's tert-butyl, that's bigger than the methyl. So this Gaussian interaction is going to be smaller than that one. So I pick the Newman projection that is going to be most stable. That's what then leads to my most stable alkene, which is going to be E or trans. So originally, I was going to have the Z alkene. Here I get the E is the only one formed. Or is the major product, I guess I should say. There will be a little bit of Z that can form, so it's considered a minor, but it's going to be way minor, like very little, like 10% to 90%. Like if you get any of it, it's very small. As opposed to above, this is the only product because remember, to do your E2, it must be antiperiplanar. So this is the only option, so that is the only product. Here I have a choice, and because I have a choice, then I get major and minor. That's the difference, is I have a choice, so then this becomes my minor product. Not the major. Does that make sense? Okay. If we look at this on a ring, we must have our leaving group axial. The reason that our leaving group must be axial is because when you're equatorial, your antiperiplanar position is the carbon. So the only way to get it to be that antiperiplanar with the hydrogen is when you are axial. Equatorial is aligned, it's parallel to the bond in the ring, not the hydrogen. So that's why in order to do the E2, you must have your leaving group axial. So when we're comparing these two rings, both of these are going to be locked. Ooh, quick, what's the relationship between them? Okay, maybe not quick. What's the relationship between them? What's different? That bromine is axial versus equatorial, right? What about that tert-butyl? Does it move? No, so it stays the same. Okay. So I see a cis and a trans. So what is the relationship going to be? If you have cis and trans? Geometric isomers. Yes. So they're geometric isomers. Why are they not diastereomers? Yeah. So they're not diastereomers. So theoretically, we've changed one but not all, is what it looks like. But it's not a diastereomer. Why is it really only geometric? Yeah. So it's, if I draw it planar, maybe that'll help. Why are these not diastereomers? Yeah. It's not chiral. We don't have a chiral atom, right? So because each carbon has bromine, hydrogen, and then left side and right side are exactly the same, there are no chiral atoms. There are no chiral atoms, you are not a chiral molecule. If you're not a chiral molecule, you can't have those optical isomer relationships. So it's not a diastereomer or an enantiomer. If it had been a 1,3 substituted, like it was on our last exam, then it could be both a geometric isomer and diastereomers. Then you could get both. But that's not what we see here. Because there are no chiral atoms, it is not going to be diastereomers. It is just geometric isomers. We're just seeing cis and trans. Okay. So looking at our geometric isomers, we see that that tert-butyl is always equatorial. So these are the most stable conformations for both of these structures. These are not chair flips, right? They have the exact same core, and they truly are just geometric isomers. You have cis and you have trans. They are the more stable chair because the tert-butyl, the large group, is equatorial. Tert-butyl hates being axial. Tert-butyl is massive. So the most stable chair is going to be when the tert-butyl is equatorial. For the chair on the left, that's perfectly fine because that puts the bromine axial, which is what I need. So now it's locked in the conformation where I get the antiperiplanar alignment. So that happens very quickly. That's fast to do that E2. This side is slow. It's so very slow because in order to have the reaction occur, I have to do a chair flip that forces that tert-butyl to now be axial. So I'm going to get a massive 1,3 diaxial interaction. So this is unfavored, but that's necessary to actually get to that product. Because then I get that antiperiplanar alignment. Cool. So E2 must be antiperiplanar. And with our rings, we get this extra consideration of the chair stability in terms of you got to get your leaving group axial. So you can see different rates in the E2 based on whether or not you can get that leaving group axial to do the E2, to be antiperiplanar. All right. So speaking of rates, let's talk about our elimination factors. So when we look at, I'm going to scroll back up for a hot second just to emphasize which ones are the same. So when we look at the E2 rate, base strength is going to be the same thing as the SN2. The stronger base is going to be faster. So that is normal. It's the same kind of thing as the SN2. For leaving group ability, you again need a good leaving group. So the better leaving group is going to be faster. Again, same as SN2. The point that is different is going to be our substrate structure. So for SN2, it was primary was faster than secondary, which was faster than tertiary. For our E2, we're going to see the opposite trend, where tertiary is going to be faster than secondary, which is faster than primary. That's the opposite of SN2. So because this is the unique identifier, that's what we're going to talk about, is that substrate. So I just want to point out that the other two factors are just the same. That's why we're not going to talk about them. But what we're about to talk about is that substrate effect. So having more substituents now is faster. So when we look at this, the alpha carbon is the one that has the leaving group directly connected to it. That's our alpha carbon. Beta is the one that's one away. When we're doing SN2, when we're doing that substitution, we're trying to get our nucleophile to get at that alpha carbon. So then this is hard trying to do tertiary because of sterics. So sad face because sterics. Right? That's why SN2 preferred the primary, was because it was trying to get at that alpha carbon, trying to get at the carbon that had the leaving group. There's a lot of stuff around it. It's hard to access it. It's hard to get there. For E2, I'm not trying to get that alpha carbon, right? I'm attacking the hydrogen next door. So I don't care how congested and hard it is to get here, because I'm not trying to get there. I'm trying to get here. So the more substituents I have, now I'm getting more opportunities to promote the elimination. Because for the elimination, I'm trying to go next door. So that's what we're seeing here, is for the SN2, if I have the hydroxide as this case, I'm trying to attack that alpha carbon. I can't do that because of sterics. So for SN2, fewer substituents, less substituted carbon was better. That was faster. For E2, I'm looking at how many beta hydrogens do I have? So in this case, let's take the one that's a little bit closer. E2 is the more beta hydrogens I have, the faster it's going to be. Because now if I have more substituents, I have more beta hydrogens. Now it's like a statistics, it's a probability thing. If I just have more options, I'm gonna be faster. So having more substituents is now favorable for E2 because now I have more options to pick from. That's faster. I don't care about sterics for the E2 in terms of my alpha carbon. The alpha carbon sterics are not an issue because I'm not attacking that alpha carbon. I attack next door. So I should say sterics at the alpha carbon are not an issue because I'm not attacking the alpha carbon. Sterics will still play a factor, but not at the alpha carbon. So then what that looks like is, for this first one, for my primary leaving group, I see 3 beta hydrogens, right? Because alpha is the one that is directly connected to the leaving group. So I'm looking next door for the beta. There are 3 hydrogens there. So I have 3 beta hydrogens when I'm primary for this molecule. When I go to my secondary, now I get 6 beta hydrogens. When I go to my tertiary, this tertiary, I get 9 beta hydrogens. So as I increase the number of beta hydrogens, I increase the rate for E2. This is the opposite of SN2 because you attack next door. You're not trying to attack that alpha carbon. So having more alpha carbon, or more beta hydrogens is going to be a faster E2 because we're not going at the alpha, we're going at beta. We attack next door. With E2, because we're attacking next door, not that alpha carbon, we might have a choice. We now get regioselectivity. The question is, all right, well, which beta hydrogen do I take? Do I take it from the left? Do I take it from the right? Like, which one am I going to attack? So when you have multiple sets of non-equivalent beta hydrogens, meaning it's not symmetrical, then we must consider regioselectivity. Which region will react? Which hydrogen do I take? It is going to be a balance or a tug of war or a battle of sterics and stability are going to be the 2 factors that we need to consider. So when I look at this, I see, oops, there are those 6 equivalent hydrogens. So these are all attached to methyls. They're both one away from that bromine. So these are all equivalent. Oops. These are equal to each other. On the right-hand side, I see that there are 2. Now I have a CH2. Now I have a methylene. I have a CH2. So now I have non-equivalent. I have different types of hydrogens. So now the question is, all right, do I take it from the left or the right? Because if I take it from the left or up, then I'm going to end up with a 1 disubstituted alkene in this case. This is going to be less stable. But it's going to happen fast. I want to flip these labels and put it there. Okay, so it's faster because probability is on my side, right? I have a whole bunch of them to take, but I'm less stable. That means that this is going to be my kinetic product. If I take it from the right-hand side, now I get a tri-substituted alkene. So that is going to be slower because there are fewer hydrogens to take from, but it's going to be more stable. So that is the thermodynamic argument. So kinetic is that speed, how quickly it forms. Thermodynamic looks at the stability of that product. So the tri-substitute is the thermodynamic product because it's more stable. The di-substituted product is the kinetic product because it happens faster because there are more beta hydrogens to take from. So to know which one we do, which one do we form, it's going to depend on the identity of our base. We want to form the more stable alkene. That's favorable. You want to make the more stable thing in general. That's like generally where you're trying to go in life or in our chemical reactions. We're trying to make the more stable product. That's what we want. But your base needs to be able to get there. So if you have a non-bulky base, non-bulky meaning it is smaller, then we're going to make that Zaitsev product, which is our thermodynamic product. So if it is non-bulky, that means that the base is going to be able to easily get in, take those hydrogens, and make the more stable alkene. So non-bulky base makes the Zaitsev product as the major. When you have a bulky base, then sterics matter. Now, I'm only going to be able to get at the side that I can more easily access. If I have a really big base, I can only get in where I can fit. So I'm only going to be able to get in on one of these open sides. So with a bulky base, I'm going to make the kinetic product. I'm going to make the Hoffman product. As my major. So to know which regioselective product we're going to make, which side we come from, is going to depend on if you have a bulky base or not. Non-bulky, take from the side that is more substituted, because if you are smaller, you can get on the side that has less hydrogens to make the more stable alkene. If you're a bigger base, you can only come from the side where it's easier to get at it, so then you're going to make the less substituted alkene, the less stable alkene. And hopefully you're wondering, what are bulky bases? These are pretty much the 3 bulky bases you need to know. So essentially, if it's one of these, it's a bulky base. If it's not, it's a non-bulky base. So our bulky bases are those tert butyls. If you see tert butoxide, if you see that O TBU minus, I want you to immediately think E2. So it's both having that tert butyl and the O minus. That together equals E2 because it's a strong base and bulky. So E2 and specifically the Hoffman product. The less substituted alkene. If you see it's neutral, like tert-butanol, then don't immediately think E2. You're doing elimination, but you're probably doing E1. So that's our tert butoxide, and it doesn't matter what your counter ion is, whether it's potassium, sodium, whatever makes you happier. So seeing that OTBU minus, or TBUO minus, is going to be our strong bulky base. Other bulky bases are diisopropylamine, or DIPA, is going to be where you have this, come on, I don't know if I need to do an update or something. My iPad's been really bad for the last several days. You get the 2 diisopropyl, so di, iso meaning split, so di meaning 2, iso meaning that Y shape, propyl meaning 3 carbons, amine meaning it's attached to a hydrogen, so diisopropylamine or DIPA, or triethylamine, so tri meaning 3, eth meaning 2, ol meaning substituents, so I have 3 2-carbon substituents, coming off of my amine, off my nitrogen. So that's sometimes abbreviated TEA, is triethylamine. So these are our bulky bases. So they're really sterically encumbered bases. All right. Are there any questions about E2 before we move on to E1? Cool. So E1 then is going to be 2 steps. E1 is 2 steps. We're going to get carbocation intermediates. So my rate is only dependent on the substrate, on the electrophile. When I look at my potential energy diagrams, the rate determining step, the slow step, is always that first step. It's always making the carbocation. That's always the slow step. Same thing as SN1. Your rate determining step, your slow step, is making the carbocation. That's always hard. The carbocation formation will also always be endothermic. I don't remember if I said that with SN1, but because it's that high potential energy, it's always going to be endothermic. So then your transition state, anytime you're making a carbocation, you'll always be able to know that it's always going to be a late transition state. You always need to look more like your product of that step. So we're going to get a partial positive on that carbon, partial negative on the leaving group because it looks more like the carbocation that exists. And I know that this is going to be a long bond because it looks more like the thing where the bond doesn't exist. So carbocation formation is always going to be endothermic. You always have to put energy in to make your carbocations. It's always going to be harder to do that. That's why it's the slow step. Your second step, doing that deprotonation, is then going to be really fast, and it leads to your more stable product. So when we look at the transition state for the second step, I have the partial bond being formed between the base and the hydrogen, partial bond being broken between the hydrogen and the carbon, and then the partial double bond being formed between the 2 carbons. It is an early transition state, meaning it looks more like the starting materials of that step. So then I need to have that partial positive there, and I'm assuming my base has a negative charge. I should add that in because I'm giving that base a partial negative. So I'm assuming that it's something like tert butoxide or whatever, having that partial negative. And then because it's an early transition state, I again can assume that my double bond, that pi bond, is going to be short. That's not how you spell short. The carbon-hydrogen bond exists, so that's going to be long. And then the hydrogen base bond is also going to be short because it doesn't exist yet in the early transition state. That's how we're using that Hammond postulate. Do you have a question? No, it's all right. I mean, if you have a question, other people probably do as well. So it's not formed yet. Oh, you're right. No, that's, yeah, thank you. See, I'm so glad you asked that question because I mixed it up in my brain. If it's not formed yet, it's long. Thank you. I'm really glad that you asked the question. If it's not formed yet, it's long. If it is formed, it's short and long. Thank you. I'd like to pretend like that was a trick, but it's not. I also need a fall break. Okay. Do we have any other questions? Okay. All right, so since E1 is only based on our substrate, our rate is only going to be based on the substrate. So that's the slow step. So all we're going to care about is our substrate structure and our leaving group. We don't care about the identity of the base because the base isn't involved in the slow step. Base is in step 2. So for my substrate structure, it's going to be the same thing as SN1, where it's going to be based on our carbocation stability. So it's going to be tertiary is going to be better than secondary, which is going to be way better than primary. So we're going to say that primary and that methyl won't happen. And it's based on carbocation stability. And again, because just like with SN1, the leaving group is going to be involved in that step. Like it's, because I don't care about the base, the quality of the leaving group is now really important, more important. So I need a great leaving group. So how I affect the rate is exactly the same for SN1 and E1, which is going to make SN1 and E1 a little bit trickier in predicting those rates because they're both affected in the same sort of way. When we talk about the stereochemistry of the E1 product, so stereochemistry being cis versus trans, E versus E, E versus Z, because we're going through that carbocation intermediate, we're going to lose any sort of stereochemistry that originally existed, first of all. And then also, we're always going to make our most stable possible product because you're going to get to pick. If you're making a carbocation, it destroys any sort of prerequisite arrangement, and it's going to say, just make the most stable thing. So just like with SM1, how you got racemization, now with our E1, we're actually going to just care about our product stability. We're just going to, I guess it's not quite the same as SM1, but it's going to be E1 is going to always lead to trans as our major, or E is the major. It can make cis or Z, but it's going to be way minor. So we're like, yeah, we're not really going to do that. When we think about majors, we're thinking we're making trans, we're making E. That's the product that we're looking at for our major product. Because it's always going to make the most stable one. So that's our stereoselectivity. So stereoselectivity is talking about the stereochemistry. That's cis trans EZ is stereochemistry. Regioselectivity is the region that you take. That's the Hoffman versus Zaitsev, right? A lot of students mix these up because they both have like a question of stability. But E1 is EZ cis trans, or sorry, stereochemistry is cis trans EZ. Regioselectivity is Hoffman versus Zaitsev. So the regioselectivity is that we are always going to make the Zaitsev product. Because again, because we're going through the carbocation and the identity of my base doesn't matter, I'm always just going to go to whatever side leads to the more stable product because I don't have to worry about any sort of like steric issues. The identity of the base does not matter. So I will always make the Zaitsev as my major. So with E1, you always want the most stable alkene possible. You want to be the most substituted, Zaitsev, and all the big groups as far apart as possible, E or trans. And with our E1, we have to remember rearrangements can occur because we can make a carbocation. And every time you make a carbocation, you must look to see, can I make a more stable carbocation? So I will still get a Zaitsev product, but I have to be cautious of that rearrangement. So the mechanism is on the next slide. So first thing, I'm given a strong acid. So I'm going to protonate my alcohol, protonate my leaving group, activate the leaving group. And because it's an acid base, Bronsted acid base, I must use equilibrium arrows. Through the rest of it, I don't care if you use equilibrium or forward arrows, that doesn't matter. But for the acid base, you must use equilibrium arrows. Then we start our E1. So now I have a really good leaving group, So leaving group leaves. I get that carbocation. Every time you make a carbocation, you must stop and check, can I make a more stable one? I'm going to be able to have an alkyl shift, a methyl shift, to get to a more stable carbocation, going from secondary to tertiary. Now I'm going to do that deprotonation, where my best base in solution is going to be water. Water is going to come, deprotonate that beta hydrogen on the more substituted side to give me my alkene product. Cool. All right, any questions about E1? All right, yeah. Yes, so Hoffman would have been if you took this hydrogen. It would be here. Okay. All right, so we've laid out a lot of details about substitution and elimination, SN1, SN2, E1, E2. We had a lot to consider there. And we talked about how our reagents and our substrates are very similar. These pathways are in competition because of that. So you will likely get mixtures of products. Your job is going to figure out which one's the major, which one is most likely to happen. That's what you need to determine. So the ways to do this are going to be, first, identify the function of your reagents. We're going to look at reagents first. The reagent is your nucleophile or your base. You want to see if it's going to act as a nucleophile or base. If it's a better nucleophile, then it's going to do substitution. If it's a better base, then it's going to favor elimination. Then we're going to look at our substrate. For our substrate, if you were primary, primary was only favored by SN2. So if you have a primary substrate, then SN2 is your major. If you have, unless you don't have a nucleophile, in which case then you're not doing SN2. But theoretically, you're doing SN2. If it's tertiary, then SN1, E1, and E2 could possibly all be the majors. So that's where looking at the reagent first helps us more. And with our secondary leaving groups, you could get potentially a mix of all four. SN1, SN2, E1, and E2. So if you look at your reagent first, that should help narrow it down. Then you're going to look at your substrate, and that should hopefully get a deciding factor. Usually, you only need to go on if you have a secondary leaving group. That's when we're going to have to consider our third factor. Is we're going to go, all right, secondary, then let's consider our solvent and our temperature. If you're trying to pick between your mechanistic pathways, then you're going to consider your solvent. So if you're looking at solvent, protic is going to favor SN1 or E1. Aprotic will favor SN2 or E2. So if you're trying to pick between, do I do SN1 or SN2? Look at your solvent. Or am I doing E1 or E2? Look at solvent. If you're trying to pick between substitution versus elimination, then we're going to look at temperature. So in general, if you are cold, that will favor substitution. If you're at room temperature or hot, that generally will favor elimination, because elimination is acid-base chemistry, so it's just going to happen faster. So if you give it that extra heat, it's just going to happen really quickly. So these would be the considerations that we would pick. If you're trying to pick between 1 versus 2, look at your solvent. If you're trying to pick between substitution or elimination, look at your temperature. But again, you're doing that last. Don't start there. That is our last thing that we consider. You look at the reagent first, then the substrate, and then if you need to, then look at your solvent or your temperature. And then step 4 is going to be look at your regiochemistry or stereochemistry and draw the product. I tried to summarize these into a couple different tables. Do whichever one makes you happier. Use whichever one's more useful. Or make your own flow chart. If you don't like tables, you prefer a flow chart, make a flow chart. But this first table, keep in mind, this is also a guide. This is not, I have some students that try to think that this is like gospel. Like this is a hard and fast rule, and this is it, and this is the only way it goes. No, this is like 90% of the time this works. There are exceptions. So you need, and it's also not all inclusive. There are more molecules than what are listed here. So you need to actually consider everything holistically. But if you're not sure where to start, this table will get you there most of the time. So step 1 was look at the reagent. That means you're going to pick your column. So if you are a nucleophile only, such as chloride, bromide, iodide, cyanide, or any of your sulfides or thiols, those are nucleophiles only. These are either the conjugate bases of strong acids or they are highly polarized. So that's going to make them a nucleophile only. If you are a base only, you're looking at things like hydride or your bulky bases. So these are not polarized. Or just things in general that are stable with the hydrogen. So hydride is going to be a base only because it will make H2 gas. So it's going to take a proton and then bubble out really quickly. So hydride is going to be base only because it's really small. It'll take that proton really quickly, and as soon as it does, it forms gas and it goes away. So hydride is a base only, and then the rest of these are our bulky bases. Things that fall into the category of both a strong nucleophile and strong base. So when I said nucleophile only, that's a strong nucleophile, weak base, if you want to think about it that way. And then your base only is a weak nucleophile, strong base is that category. So it was base only because it wasn't good at being a nucleophile, or a nucleophile only because it wasn't good at being a base. So strong, where you're a strong nucleophile and a strong base, those are things with our negative charges, and small. So these are our oxides, that O minus. Keeping in mind that if you're tert butoxide, you are base only because you're too big. So every other oxide is both capable of being a nucleophile and a base. And if you are just a neutral oxygen, then you're not good at being either. You're a weak nucleophile and a weak base. You're not really good at either one. You could do either one, but you're not great at it. You have a lone pair, but you're neutral. So you pick your column first. You figure out which reagent am I, and that picks my column. That looks like I crossed out the terp-butoxide now. So once I pick my column, that narrows it down to 2 reaction pathways. So if you're nucleophile only, you're doing substitution. So then you're going to look, all right, am I doing SN1 or SN2? If you're a base only, then you're doing elimination. You're doing E1 or E2. If you're a strong nucleophile and a strong base, you're going to react right away. So you're going to do a concerted mechanism. So you're looking at SN2 or E2 because you're going to react right away. You're not going to wait around for a carbocation to form. You're going to attack. If you are a weak nucleophile and a weak base, then you're going to hang around and just wait until you get something that's more reactive. You're going to wait around for a carbocation. You're going to be stepwise. So then you're going to be SN1 or E1. So once you know your reagent narrows it down to those 2, whether you are substitution, elimination, concerted, or stepwise, then you're going to pick between those 2 by looking at your reagent, or sorry, your substrate. And then if you need to, you'll do the additional considerations. So I'm down here, so I know I'm either doing SN1 or SN2. If I'm a tertiary leaving group, I'm SN1. If I'm a primary leaving group, I'm SN2. If I'm secondary, then I look at my solvent, and then I'm going to do protic or aprotic. If I'm looking at my bases for elimination, if I'm E1, then I am going to be tertiary with protic. Most likely, if you are a strong base, you're probably doing E2 because that's where most of it happens. Pretty much the only time that you're not is when you're in that protic solvent with the tertiary really stable leaving group, or sorry, really stable carbocation. Otherwise, most of the time, if you're base only, you're doing E2. If you are a strong nucleophile, strong base, then again, we're looking at our substrate to be our defining factor because primary favors SN2, tertiary favors E2, and then for secondary, we need to look at the temperature. So if I'm cold, then I'm going to be favoring SN2. If I'm room temp or hot, then I'm going to favor E2. Stepwise, we're doing the same thing, where if we're looking at our tertiary, and to keep it uniform, I'm actually just going to get rid of that, because at room temperature, it's really like hit or miss, but to keep it uniform, we'll just say anytime it's room temperature or heated, we'll just in general favor elimination. You technically could get like both, but to make it easier, I'm just going to say room temp or heated, we're going to favor elimination. And I guess for that, we're kind of looking at 2 pathways at that point. Okay. All right. All of our reactions are also summarized down here, so I recommend reading those. And then there are some practice problems, but we'll start next week doing those practice problems. But I would do it before you do the quiz. I would do some practice problems to know which mechanism you need to pick. All right. Have a wonderful day, and have a safe break.